Introduction to Calculus, Mixed Practice 0. We are practicing for the final exam, Ms. Stewart.
Very exciting. I like it.
So I'm just going to go over Mixed Practice 0. I like to start counting at 0. All computer scientists like counting at 0.
Yeah,
0
right.
is a historical thing. All right, so we're going to go over limits. You remember the notation. This really, I'm just saying, limit as x approaches 3. I'm looking for the y value. Remember, this is what the x value is doing. I want to know what the y value is doing.
Perfect.
Very simple, really.
Input, output.
Input, output. So I'm just going to put a 3 in for my x values.
See what you get out.
Let's see what I get. So I have 3 over 3 minus 3, also known as 3 over 0.
Oh no.
Well, what do you think about that? I know the zero division police, or you have some saying.
The math police busting down that door.
You can't divide by 3, so in fact...
You can't divide by 0.
I'm sorry. You can't divide by 0, so in fact, the limit does not exist. And, and this is a multiple choice question, so all we were looking for here is does not exist. And I'm just going to abbreviate.
The limit
Does not exist. Limit does not exist. Of course, if I had 3 in the numerator,
no
the
problem.
limit would be...
You mean 0 in the numerator?
Why do I keep saying 3, Miss Stewart?
That's okay. If you had 0 divided by 3, that's just 0.
0 upstairs, okay. 0 downstairs does not exist.
Beautiful.
Now, of course, really at 3, there's an asymptote in this function, and so really what's happening is it's either going, the function's either going up to infinity or down to negative infinity. And remember, I could figure this out by plugging in something really, really close to 3 on both sides, 3.1 or 2.9, something like that. But I'm not asking for that. It does not exist. All right.
Fantastic.
Here's the next one. If I stick in a 1, I can see that I'm going to get a 0 over 1 squared minus 1 is a 0. 0 over 0. Well, that gives me a little clue. Remember what that tells me, Miss Stewart?
That tells us that you have a factor that is in the numerator that's also
Yes.
in the denominator, which you can remove.
I have a removable discontinuity. How am I going to remember that this is called removable?
I think because you're removing those factors,
Yes,
it's
now.
like you're removing an asymptote.
What's really left on top?
A 1.
I have a 1 left on top. Let's be clear about that. Right? So I remove the discontinuity, and I'm just going to stick in the 1 here. So I have 1 over 1 plus 1, also known as 1/2. Am I done?
Yeah.
Indeed I am.
So the limit as x approaches 1 is 1/2. So if that y value could exist, it would be 1/2.
That's exactly what...
It's kind of honing in from the left and the right,
now,
to a y value.
Of course, when you remove this, really that means there's a little tiny hole in the graph at x equals 1. But I'm removing it. So really, this function, for our purposes, really this function looks like the function 1 over x plus 1. That's what it looks like, but there's a little tiny hole in it there, which I removed.
Fantastic.
Anyway, okay. This is a little bit different. Limits at infinity. Remember how that works?
End behavior.
End behavior. We used to call this end behavior. Now, we're wearing our big boy pants. This is, we're talking limits now, right? Calculus.
That's right.
So limits as x approaches infinity. I just look at the controlling terms. The biggest term on top, the biggest on the bottom, the guy with the biggest exponent. So if I put in infinity on top and bottom, well, the bottom guy is squared. That's going to grow much faster than the top. So I have a comparatively small number on top and a big number on the bottom. Small over big. Well, what am I going to? Imagine if I had like 1/1,000,000th.
Wow.
Is that a big number or a small number?
That's pretty close to 0.
That is pretty close to 0.
Yeah.
So the limit in this case is...
As long as I gaze on Waterloo sunset, I am in paradise. Every day I look.
This is question 2. I have a rectangle here, width and length. This is going to be a related rate problem.
Yes, it is.
It says, and you at home can read it if you want. It says the length of this rectangle is decreasing at a rate of 3 centimeters per second. So I'm actually going to write that as dl over dt. Remember what that notation means? The length is changing over time, is really. So length is changing over time. It's getting smaller. It's changing by 3 centimeters a second. So I made it negative.
Negative because your length is getting smaller.
That's right.
Very
The
nice.
width is increasing by 5 centimeters a second. So I'll say dw dt equals 5.
Positive 5 since
Positive
it's
5,
increasing. Getting the
Right.
hang of it.
So this is how they're changing. This is how they're changing over time. And then it says right now the length is 8 and the width is 6, and I'm supposed to find how various things are changing. Like the first question says, how is the area changing?
Ah, okay.
So you still got me way over
I
here?
do.
Okay. So I'm just going to write the area equation of a rectangle. Area, of course, is length times width. And I want to know how this is changing. Rate of change, slope,
Derivative.
Isn't that the answer to most of these questions?
That is the answer
blah,
to
blah,
most
blah,
of these.
find the derivative, more blah, blah, blah.
Exactly right.
So this is the blah, blah, blah part. Now I'm going to take the derivative of this. The derivative of area, dA dt. The derivative of length times width. Remember how this works? That's a tricky one.
Product rule.
It's a product rule. So that's the derivative of the first guy, the derivative of L, which is
L dt.
L dt, times the second guy,
As it is.
plus the first guy. You really got me way over here?
Yeah, I do.
Way over here? Wow, I'm way over here. Plus the first guy times the derivative of the second guy.
All right. That's pretty straightforward.
Right? That's pretty straightforward. And then I just fill in my numbers. I'm done.
Okay. dA dt. That's what you're looking for.
I'm looking for how the area is changing. The LDT is -3.
-3. It's nice to have it all labeled. It makes it nice and easy.
W is 6.
At this
I think
instant.
that's going to be -18. Plus length, which right now is 8. And dW dt is
5.
yeah, 5. Thank you. So that is going to be 40 minus 18. What is that? 22, I think.
That sounds good.
Okay. dA dt equals 22, and the area is actually changing. I guess I could put units there. It must be square.
Well, we have centimeters, so it'd be square centimeters.
Square centimeters per second.
Yeah.
I'll
beautiful.
do this. Is not physics class, but what the heck?
Why not?
Square centimeters per second. I'll make Mr. Fody happy by.
So that's how fast the area is changing at this instant.
At this instant. At this instant. Sure.
Right.
Absolutely right.
Very nice.
So the next part says, how is the diagonal changing? Right.
Diagonal.
Yeah, so let's label the diagonal. You know, I guess I could call it D for diagonal,
Let's
but I'm
not.
not. There's going to be a lot of D's in
How
there.
about
as it
C?
is. How about C?
Just
for,
in terms of A,
oh,
B,
A's could be,
C.
very clever,
I'm
okay.
anticipating.
So I need some kind of equation which relates these three sides, not really a side, but these three measurements of my rectangle. What do you think, Ms. Stewart? It's going to be a good
I'm
one.
thinking Pythagorean theorem.
Yes, L squared plus W squared equals C squared. Now
Yeah.
I'm going to take the derivative. I want to know
Because-
how things are changing.
Beautiful.
So I'll take the derivative. The derivative of L squared is just 2L, but remember, I'm taking the derivative of L, which is the L dt.
dt. A little chain rule action there.
Absolutely. Plus 2W, W dt equals 2C, dC dt.
Beautiful.
Right? It's really, it is a chain rule. Let's just I'm really bringing that 2 in front. It's 2 times the coefficient, which is 2. L times the derivative of L. That's where this dl dt is, of course, coming from.
Beautiful.
And then I just fill things in
Fill
again.
things in
I'm
again.
just filling them in. Okay,
Love that.
so 2L right now is 8. dl dt, 3. 2W is 5.
6. W is 6.
Thank you. W is 6, also known as 6, okay. 5, also known as 6. All right, 6. What am I up to?
dW dt is
which
your
is
5.
To C.
Oh.
I don't know what C is right at this moment in time, so let's just leave that for the moment. And dC dt,
That's what you're looking for.
that is what I'm looking for. Well, at this moment in time, of course, I know length is 8, width is 6. I wonder if I could calculate C right now.
Yeah, I
What do
think
you
we
think?
could. We could just do the Pythagorean
I think
theorem,
we could.
or even think maybe of our Pythagorean
I
triples.
think this is. So it's going to be this squared, 8 squared is 64,
Right.
plus this squared is 36, which conveniently is 100.
100.
Square root of 100?
10.
So right now, I can calculate C is 10.
Love that. That's
Just
a
gonna
3, 4,
stick
5
that in.
triangle, I believe.
Pardon me?
3, 4, 5 triangle.
That's exactly right. Now I could just stick all these numbers in my calculator here. Of course, I could divide everybody by 2. Should I do that?
Well, no, let's just do it. Let's just do it. So we have negative 48.
You got that already?
I have that already.
Wow, you're quick. Okay.
I know. Plus 60.
Plus 60.
Equals 20 dc dt.
So that's
negative 48 plus is 12.
12, right, thank you. 12 equals
20 dc dt. I had my tea this morning, so I'm all ready to roll.
dt
12 twentieths.
20ths.
Also known
which is
as.
the same thing as 4/5.
Beautiful.
So there we go. So dc dt.
3/5.
Thank you.
Right?
Also known as 3/5.
3/5?
Yes.
4 goes into 12
3 times.
twice. 4 goes into.
4 goes into 12 3 times.
You know, this is all the arithmetic. We're math people, not so much arithmetic people.
I know. Everyone thinks because I teach math, we go out to eat and I should be one splitting the bill or something.
Which I'm sure you can do just fine.
Right.
All right, beautiful.
All right.
What are our units there, just for fun?
This
Make Mr. Fody
this
happy.
is a linear thing, so
Yeah.
this is just centimeters a second.
Centimeters per second. And that's the rate at which the diagonal is changing
And
at
it is
this
increased.
instant. Love it.
Thank you. Finally, I want to know how the perimeter is changing.
Fantastic.
So yeah, there we go. Perimeter of a rectangle, I'm just going to add up all the sides.
Yeah.
W plus W, also known as 2W. Can I just do that in
I
one
think
step
you
there
can.
for you? Okay.
We're good.
Length plus length, I'm going to call that 2 length.
Fabulous.
The derivative, sometimes it confuses students.
Yes, it
The
does.
derivative of 2W, oops, sorry, I'm gonna mess here. The derivative of P, let's do that first, dP dt. The derivative of 2W is just 2
Right.
times the derivative of W, dW dt. Sometimes students want to stick in a W there,
Yeah.
2W dt. Well, you don't do that. I mean, of course, like if I had some function like this, f of x equals 2x,
Derivative of that is just 2.
it's 2.
It's 2.
It's just 2. Times the derivative of x, which is just 1, we don't write it.
Right.
But it's x's.
Yeah.
Like that. But now we're doing related rates, so in fact, we have to add on the derivative of w, which is not going to be
Good.
1, perhaps not anyway. So the derivative of 2L is 2
2.
dL dt.
Very nice. Now we just plug stuff in.
Stick it in. Okay, so I'm looking for the rate of change of perimeter. 2 dW dt is 5.
Fantastic.
Plus 2 dL dt is negative 3. So the perimeter is changing, dP dt. 10 minus 6, also known as 4. And this is going to be, again, centimeters per second. This is a linear.
So this is interesting because we didn't care about what the length or the width was.
That is correct. And you know, it makes sense, of course, that, I mean, the length is the length increasing, the length is decreasing at some constant rate, and width is increasing at some constant rate. So the perimeter is changing at some constant rate, no matter how big the thing is at some moment.
Yeah, so it doesn't depend on how big or small the rectangle is when you're finding the rate. You could even do it without calculus.